Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a nice exponential equation with complex numbers. First of all, why is this equation considered nice? Because I said so. Not only that, but it's also we have a negative number on the right hand side, which makes it more interesting. And we're going to take a look at the graph first and then proceed with the solution, and at the end I'm going to show you the solution from Wolfram Alpha. Do you think Wolfram Alpha can solve this problem successfully, at least as much as we do? Okay, so we have something like this, e to the power z. What is z, by the way? Z is a complex number. Complex numbers can be written as a plus bi. It's also the name of this channel, where a and b are real numbers, and I squared is -1. If you're new to complex numbers, go ahead and check out my lecture videos, because I made a number of videos, I think 9 of them, on basics of complex numbers. Go ahead and check him out. I also have another channel which is called Cyber Math, cyber with an S, where I do number theory and algebra problems. I'm thinking about the geometry problem, but it's taking forever to set up. Anyways, so this is my equation. We're going to solve it. Z is a complex number. So can we just replace z with a plus bi then? Because sometimes we use that method. Yes, you can do that. But then how are you going to use that information, right? I mean, we're going to end up using the natural log anyways, or the exponential function anyways, so it's not going to matter. So let's go ahead and forget about it. But is this an advantage? I don't think so. I could be wrong though all the time. Correct me if I'm wrong. So here's what we're going to do. First of all, notice that, did I say that I was going to show you a graph? Yes, I did, right? So here's the graph of e to the power z, and the -2. But this is for real values, of course. I mean, Desmos cannot graph complex functions, or can it? I mean, if it does, let me know, because I'm always looking for a complex plotter and I haven't found a good one. Well, I think Wolfram Alpha can do it, but I'm not exactly sure how the syntax works, and I'm kind of lazy to check. Too lazy to check. Anyways, so for this shows us e to the power z equals -2 has no real solutions. And why is that? Because e to the z is always positive if z is real. But if you go to another world, e to the z can be negative. That's what makes this problem interesting and complex. That's why it's a good fit for this channel. Now, let's see how we can solve these kinds of problems. I'm going to give you more of a kind of like a general approach, or you can apply it to other situations, scenarios. First of all, notice that we can't just log both sides. I mean, we can. Why not, right? But then you're going to end up with something like this. What is ln of -2? Undefined. Too bad. Well, if you look at the ln function, again, for real values, it's not defined for 0 and negative numbers. It's only defined for positive reals. But that's for the real world. Who cares, right? We're not interested in the real world. We're interested in a complex world. So let's complexify things. Instead of going with the ln, obviously we could proceed this way, but a better way to do it is kind of like a more rigorous, is to write -2 in the complex world. In other words, as an exponential. Can we do that? Yes. Every number can be written as an exponential, even a plus bi. How? Euler said e to the power I theta equals cosine theta plus I sine theta. This is the standard form, so you can consider this a plus bi, but the caution, the modulus, or the absolute value for this number, is 1. You know why? Because cosine squared plus sine squared is always 1, regardless of the values of sine and cosine. Yes, they depend on each other, but their squares always add up to 1. Okay? So how do we go from this to ln of -2, or just to -2? Think about it. How would you write this? How would you write -2 in that form? Think about it. For that, you would need this to be -2 and this to be 0. Right? No, incorrect. You know why? Because, first of all, that would be very problematic, because sine squared plus cosine squared equals 1 is not satisfied with these values, right? So you're saying something contrary to what is standard. So this is not going to work. The problem, again, is the modulus, because if you take the absolute value of -2, you don't get 1. So this only applies. So more general form is going to look like this. Why don't you multiply both sides by r? And then, yes, you can do this, right? Now, if you set it equal to negative 2, can we find it from here? Maybe. R cosine theta is negative 2. R sine theta is 0 because the imaginary part is 0. Doesn't this show that sine theta is supposed to be 0 here? I think so. There are two angles for which sine is 0. One of them is 0 or 2 pi or any multiple of 2 pi like 2 pi n. The other one is just pi or plus 2 pi k, right? If you look at the principal values or the smallest values, this would give you 0, this would give you pi. So at those points, okay, what about that? We need to look at the first equation too. What about r cosine theta is equal to negative 2? Then r is probably 2 because r can't be negative. And this needs to be negative 1 because, come on, we're talking about a real theta here, right? If cosine theta is negative 1 and sine is 0, that can only happen at pi. So pi is our choice. Pi is a winner. Yay, pi wins. So now we have 2 times e to the power I pi, which negative 2 writes. But if you don't like that, my approach was an alternative approach, by the way. I haven't used this before. You can plot negative 2 on the argand plane, which is a fancy name for the coordinate plane when you write real and imaginary axes like this. And then connect it to the origin. That's going to give you your modulus, but that's just going to be 2 units. And then looking at the angle, that is pi radians. And of course, you can always multiply or add multiples of 2 pi. That's the period, right? Cool. So I pretty much got the same thing, but in a more general form, I should add 2 pi n multiples of 2 pi. Make sense? So that's the more general form. If you want the principal value, then because this is multi-valued. In the polar form, of course. Negative 2 is not multi-valued as when it's written like that, but when you write it the exponential form, then it's multi-valued. So what am I doing? I'm just setting this equal to that. So e to the z equals negative 2, which is 2 times e to the power I times pi plus 2 pi n. And I should leave some room. I should have known, but no worries. I can still move stuff. He used to cut it, but now it's not cutting it. That's good. Now I can go ahead and natural log both sides, can't I? And when I do, of course, use parentheses sometimes, right? Move the z, that gives you z. And then this is a product, so you can kind of write it as ln 2 plus, when you ln e, it's 1, so it's going to be I times pi. You should probably write it like this. It's not a fraction. Pi plus 2 pi n. Oh, I forgot to say n is an integer. You knew that, right? Great. So that's my solution. So here's the thing. Now, e to the ln 2, if you think about it, e to the ln 2 is 2. Where does the negativity come from? From the imaginary world, from the imaginary part, of course. I pi or e to the I pi is always negative 1. That's how you can complexify negative 1 in the complex world. Anyways, so that should be our solution. Do you think Wolfram alpha can solve it? Or if you wanted to get the principal value, replace n with 0 and you'll get the answer. But let's go ahead and check out what Wolfram alpha provides and compare it to our answer. Remember that, okay? Take a screenshot. Now let's go to Wolfram alpha. I mean, the screenshot from Wolfram alpha, And ta-da! Wolfram alpha can solve it, but it just expresses it in a little different way. Notice that negative I squared is 1, so that gives you positive ln 2. Unfortunately, Wolfram alpha names it as log, but I use log for base 10, not for e, unfortunately. Or fortunately. Anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.